There is no code requirement mandating a disconnect for a transformer. This is a common misconception in the electrical field, but the National Electrical Code, or NIC, does not universally require a disconnect switch to be installed directly at or near a transformer. The need for a disconnect is determined by several factors related to the transformer's application, its voltage levels, and the specific requirements of the electrical system it serves. Firstly, consider the primary and secondary voltage levels of the transformer. Transformers are used to step up or step down voltage, and the voltage level on either side significantly influences the types of protection and disconnects needed. For instance, a high-voltage transformer in an industrial setting might have different requirements than a low-voltage transformer serving residential loads. Secondly, the accessibility of the transformer is a crucial factor. If the transformer is readily accessible to qualified personnel, the requirements for a local disconnect might be different compared to a transformer located in a difficult-to-reach area. The NEC prioritizes safety and ease of maintenance, so accessibility plays a key role. Thirdly, the overcurrent protection for the transformer is a significant consideration. The NEC outlines specific rules for overcurrent protection devices, or OCTs, such as fuses and circuit breakers, designed to protect the transformer from overloads and short circuits. These OCTs might serve as the disconnecting means, fulfilling the code's intent without requiring a separate disconnect switch. The NEC Article 450 provides detailed guidelines for transformers, including their installation, protection, and ventilation. However, within Article 450, you will not find a blanket statement mandating a disconnect for every transformer. Instead, the code focuses on ensuring that transformers are protected from overcurrent and that there are adequate means to de-energize the transformer for maintenance and repair. Section 450.3 specifically addresses overcurrent protection. It details the requirements for protecting transformers based on their voltage rating and impedance. These requirements ensure that the transformer is adequately protected from faults and overloads, which is a primary safety concern. To understand why a disconnect isn't always required, let's consider a common scenario: a small low-voltage transformer used in a control circuit. This transformer might be protected by an upstream circuit breaker that serves as the disconnecting means. In this case, the circuit breaker fulfills the requirement for disconnecting the transformer from the power source, making an additional disconnect switch redundant. However, larger transformers, particularly those serving critical loads or operating at higher voltages, often benefit from having a dedicated disconnect switch. This allows for easier and safer maintenance as it provides a clear and local means of de-energizing the transformer. The decision to install a disconnect switch often comes down to a risk assessment, considering factors such as the potential hazards associated with the transformer, the frequency of maintenance, and the qualifications of the personnel who will be working on the equipment. Moreover, local codes and regulations can influence the requirements for transformer disconnect. While the NEC is a widely adopted standard, local jurisdictions might have amendments or additional requirements that mandate disconnects in certain situations. It's essential to consult with local electrical inspectors and authorities to ensure compliance with all applicable regulations. For example, some jurisdictions might require a disconnect for all transformers exceeding a certain kilovolt-ampere rating or those installed in specific types of occupancies. Also, consider the specific application of the transformer. Transformers used in hazardous locations, such as those containing flammable materials, often have stricter requirements for disconnects and other safety measures. These requirements are designed to minimize the risk of ignition and explosion in these environments. The NEC Article 500 and subsequent articles address electrical equipment in hazardous locations, providing detailed guidance on the types of equipment and wiring methods suitable for these areas. Now, let's delve into scenarios where a disconnect is typically recommended or required, even if not explicitly mandated by a general code provision. Firstly, consider transformers supplying emergency systems. The NEC Article 700 addresses emergency systems and requires that these systems have a reliable source of power and the ability to be quickly disconnected in case of an emergency. Therefore, A disconnect switch for a transformer supplying an emergency system is often necessary to comply with these requirements. This allows first responders and maintenance personnel to quickly isolate the transformer and ensure the safety of the emergency system. Secondly, transformers located in areas with limited access or high traffic might benefit from a disconnect switch. In these situations, a local disconnect can improve safety and reduce the risk of accidental contact with energized parts. The disconnect provides a clear and easily accessible means of de-energizing the transformer, minimizing the potential for electrical shock or other injuries. Thirdly, transformers serving critical loads, such as those in hospitals or data centers, often require a disconnect switch to facilitate maintenance and minimize downtime. These facilities rely on a continuous power supply, and any interruption can have significant consequences. A disconnect switch allows maintenance personnel to safely work on the transformer without disrupting power to the entire facility. In summary, while there is no specific code requirement for a transformer to have a disconnect in all scenarios, several factors influence the decision. These factors include the voltage levels, accessibility, overcurrent protection, local codes, and the specific application of the transformer. It's crucial to conduct a thorough risk assessment and consult with qualified electrical professionals to determine the most appropriate and safe solution for each installation. Always prioritize safety and compliance with all applicable codes and regulations. The absence of a general mandate does not negate the importance of sound engineering judgment and adherence to best practices in electrical design and installation. The code provides a framework for safety, but it's the responsibility of the electrical professional to apply that framework intelligently and responsibly. For a deeper understanding, consider the following points regarding transformer installations and disconnects. 1. Understand the transformer nameplate. The transformer nameplate provides critical information about the transformer's voltage, current, and kilovolt-ampere rating. This information is essential for selecting the appropriate overcurrent protection and disconnect devices. 2. Consider the transformer's inrush current. Transformers exhibit a high inrush current when initially energized. This inrush current can be several times the transformer's normal operating current and can trip overcurrent protection devices if they are not properly sized. 3. Ensure proper grounding. Proper grounding is essential for electrical safety. The transformer's grounding system should comply with the NEC Article 250, which provides detailed requirements for grounding and bonding. 4. Provide adequate ventilation. Transformers generate heat during operation. Adequate ventilation is necessary to prevent overheating and ensure the transformer's longevity. The NEC Article 450 provides guidelines for transformer ventilation. 5. Use appropriate wiring methods. The wiring methods used to connect the transformer should comply with the NEC and be suitable for the voltage and current levels involved. 6. Ensure proper labeling. Transformers and disconnect switches should be properly labeled to identify their function and voltage levels. This helps prevent confusion and ensures that personnel can safely operate and maintain the equipment. 7. Conduct regular inspections. Regular inspections of transformers and disconnect switches are essential to identify potential problems and ensure that the equipment is operating safely. 8. Maintain accurate records. Accurate records of transformer installations, maintenance, and inspections are essential for tracking the equipment's performance and ensuring its long-term reliability. Let's consider a specific example to illustrate these points. Suppose you are installing a 75 kV 480 volt 208/120 volt transformer in a commercial building. The transformer is located in a dedicated electrical room and is readily accessible to qualified personnel. In this scenario, you would need to select overcurrent protection devices that comply with the NEC Article 450.3. Depending on the transformer's impedance, you might be able to use a circuit breaker as the disconnecting means. If the circuit breaker is readily accessible and clearly labeled, it could serve as both the overcurrent protection and the disconnecting means, eliminating the need for a separate disconnect switch. However, If the circuit breaker is located in a remote location or is not easily accessible, you might consider installing a local disconnect switch near the transformer for added safety and convenience. The decision would depend on a careful evaluation of the specific circumstances and a thorough risk assessment. The absence of a strict code mandate for a disconnect does not diminish the importance of safety and best practices. It's always prudent to err on the side of caution and install a disconnect switch if there is any doubt about the safety or convenience of the installation. Remember that the NEC is a minimum standard, and electrical professionals are encouraged to exceed these standards whenever possible to enhance safety and reliability. Moreover, consider the long-term implications of your decisions. A well-designed and properly installed electrical system will not only comply with the code but also provide years of reliable and safe operation. Take the time to carefully plan your transformer installations and consult with experienced professionals to ensure that you are making the best choices for your specific application. Furthermore, let's consider the impact of energy efficiency on transformer disconnect decisions. While not directly related to code requirements, the ability to easily de-energize a transformer can be beneficial from an energy-saving perspective. In situations where a transformer is lightly loaded for extended periods, the core losses can represent a significant portion of the overall energy consumption. By installing a disconnect switch, it becomes easier to de-energize the transformer during periods of low demand, reducing these core losses and improving overall energy efficiency. This is particularly relevant in facilities with variable load profiles, such as office buildings or manufacturing plants. Consider a scenario where a transformer is sized to accommodate peak loads that occur only during certain times of the day. During off-peak hours, the transformer may be operating at a small fraction of its rated capacity. In such cases, the core losses can be a significant drain on energy resources. By installing a disconnect switch, the facility manager can easily de-energize the transformer during these off-peak hours, reducing the core losses and saving energy. While this may not be a primary driver for installing a disconnect, it can be a valuable secondary benefit. In addition to energy efficiency, consider the impact of transformer maintenance on disconnect decisions. Regular maintenance is essential for ensuring the long-term reliability and performance of transformers. This maintenance may include visual inspections, testing of insulation resistance, and tightening of connections. To safely perform this maintenance, it is necessary to de-energize the transformer. A disconnect switch provides a convenient and reliable means of de-energizing the transformer, making the maintenance process easier and safer. Without a disconnect switch, it may be necessary to de-energize the entire electrical system to perform maintenance on the transformer, which can be disruptive and costly. Consider a scenario where a transformer is located in a critical facility such as a hospital or data center. In these facilities, downtime is unacceptable, and any interruption to the power supply can have serious consequences. By installing a disconnect switch, maintenance personnel can safely work on the transformer without disrupting power to the entire facility. This allows for proactive maintenance to be performed, preventing potential failures and ensuring the continued reliability of the power supply. The disconnect switch provides a clear and easily accessible means of de-energizing the transformer, minimizing the risk of electrical shock or other injuries. Let's also discuss the role of arc flash studies in determining the need for transformer disconnects. Arc flash is a dangerous phenomenon that can occur when a short circuit fault occurs in electrical equipment. The resulting arc can generate intense heat and pressure, causing severe burns and other injuries. Arc flash studies are conducted to assess the potential hazards associated with arc flash events and to determine the appropriate safety measures to mitigate these hazards. One of the key outputs of an arc flash study is the determination of the arc flash boundary, which is the distance from the equipment where the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for a second-degree burn. Arc flash studies can influence the decision to install a transformer disconnect. If the study reveals that the incident energy levels are high, it may be necessary to install a disconnect switch to reduce the risk of arc flash injuries. A disconnect switch can be used to energize the transformer before performing maintenance or other work on the equipment, reducing the potential for an arc flash event. The disconnect switch should be located outside the arc flash boundary, allowing personnel to safely de-energize the transformer without being exposed to the hazards of an arc flash. Consider a scenario where an arc flash study reveals that the incident energy levels at a transformer are high due to the upstream overcurrent protection devices having a long clearing time. In this case, installing a disconnect switch with a faster clearing time can reduce the incident energy levels and improve safety. The disconnect switch can be equipped with fuses or a circuit breaker that is sized to quickly interrupt the fault current, minimizing the duration of the arc flash event. The disconnect switch should also be properly labeled with the arc flash hazard information, including the incident energy levels, the arc flash boundary, and the required personal protective equipment, or PPE. Finally, let's delve into the importance of coordination studies in conjunction with transformer disconnect decisions. A coordination study is an engineering analysis that ensures the proper selection and coordination of overcurrent protection devices throughout an electrical system. The goal of a coordination study is to ensure that the overcurrent protection devices closest to the fault will operate first, minimizing the extent of the outage and preventing unnecessary tripping of upstream devices. A well-coordinated electrical system will improve reliability, reduce downtime, and enhance safety. Coordination studies can influence the decision to install a transformer disconnect. If the study reveals that the overcurrent protection devices are not properly coordinated, it may be necessary to install a disconnect switch to improve coordination and reduce the risk of nuisance tripping. A disconnect switch can be used to isolate the transformer from the rest of the electrical system, allowing for independent testing and maintenance of the overcurrent protection devices. The disconnect switch can also be used to sectionalize the electrical system, preventing a fault in one section from affecting other sections. Consider a scenario where a coordination study reveals that the upstream overcurrent protection device for a transformer is tripping unnecessarily due to inrush current or temporary overloads. In this case, installing a disconnect switch with a time delay feature can prevent nuisance tripping and improve the reliability of the electrical system. The time delay feature allows the disconnect switch to ride through temporary overloads without tripping, while still providing protection against sustained faults. The disconnect switch should be selected to have a suitable interrupting rating to handle the available fault current at this location.